Our last section in this chapter, and the fifth of the 5 skills that we need to think about from chapter 19, has to do with the solubility of ionic compounds. Remembering that not all salts completely dissociate into their ions. For things that don't completely dissociate, we call them slightly soluble. And there's actually a whole range of sample problems that we can work through. Thankfully, they're not as involved as our buffer or our titration problems, but they range from all of the aspects of equilibrium that we've already discussed in our previous chapters, in chapters 17 and 18. Writing equilibrium expressions, kind of both types of equilibrium problems, calculating a K or using a K to determine equilibrium parameters. And then we have a few really interesting kind of applications, thinking about common ion effects, being able to predict solubility when we add a strong acid, and that's really kind of thinking about a Le Chatelier's principle effect. Using this to predict whether certain conditions will allow a precipitate to form. Using a molecular seams problem to precipitate, or to think about whether a precipitate were formed. And then finally, kind of an application of thinking about separating ions by something called selective precipitation. So quite a few different kinds of problems that we'll see with this solubility. And to remind you, when you see KSP, that SP stands for solubility product. So that reminds us that we're talking about the solubility of ionic compounds. Okay, so the first sample problem here is pretty straightforward. It's just learning how to write ion product expressions. So this is, how to write a Q or a K value, just like we learned in chapter 17. And we're going to treat this the same way. We always want to write an equation for what we're thinking about. And then after we do that, we use that equation to write our equilibrium expression. Now, one of the things that you do have to know for this chapter is that we have to remember from chapter 4, how do we name ionic compounds? So for example, if it says magnesium carbonate, what is magnesium carbonate? We need to know that magnesium carbonate is MgCO3. So we have MgCO3 as a solid. It is slightly soluble, which means in an equilibrium sense it dissociates to magnesium ions and carbonate ions. To write a KSP, it's just like we've always done before. It's a concentration of products over reactants. But one of the things that's unique with these problems is our reactants are always going to be a solid salt. We never include pure solids or liquids in our equilibrium expressions. So basically, it's just going to be the reactants. But one of the things that we will start to see here that we haven't seen in some time, we don't happen to see it with this first problem, is we will have coefficients that we need to consider with the ions that we form, and those again will become exponents in our equilibrium expressions. All right, so that's magnesium carbonate. Iron hydroxide, specifically iron 2 hydroxide. So we need to remember that iron 2 means it's an iron with a 2+ charge, and we need to know that hydroxide is a -1 charge. Hopefully remember that from our buffers and our titrations. But this means that we're going to have FeOH2 as our solid salt. When this dissociates, it breaks apart into iron ions and 2 hydroxide ions. So the KSP here is going to be equal to the concentration of iron times the concentration of hydroxide squared. And we got to make sure that we remember these because we've been doing stoichiometry with our acid and base chemistry that really hasn't had coefficients. So we have to make sure we're remembering to include our coefficients in our chemical equation and use those as exponents in our equilibrium expression. All right, calcium phosphate. Calcium is 2+, phosphate is 3-. We have to do our little crossover approach to realize that the molecular or the ionic formula for calcium phosphate is going to be Ca3PO4, the quantity 2, solid. This again is going to dissociate into 3 calcium ions plus 2 phosphate ions. KSP is going to be equal to the concentration of calcium cubed times the concentration of phosphate squared. One of the things we'll see in this chapter is it's not uncommon to see 2s, 3s, 4s, even up to 10s in terms of the coefficients and thus the exponents. Last problem here have to remember that silver is +1 and sulfide is S2-. So Ag2S is going to be our starting salt. Dissociates into 2 silver ions plus a sulfide ion. Well, one of the things that we learned about is anytime we have sulfide ions, this is such a strong conjugate base that if we are in aqueous solution, we're going to generate HS-, and then that's going to leave behind some hydroxide. So really, this is truly an intermediate that we're not going to have any appreciable amount of S2- in solution. It will become an equivalent amount of HS and OH-, so the KSP will reflect those parameters. It's going to be Ag², HS, and OH-. So if you need to, make sure you go back to chapter 4 so that you're comfortable looking at the name of an ionic compound and translating it into a formula unit. If you're not able to write the name or the chemical formula for an ionic compound, you're not likely to be able to get the dissociated ion stoichiometry right, and you're not likely then to have a correct KSP that you can write.